Dear students, continuing with our lecture series on reduction of organic compounds, today we will discuss sodium borohydride reduction and other derivatives of sodium borohydride, how they affect the organic functional group transformations. So, as I have told you earlier, that reduction can be defined as conversion of an atom from higher oxidation state to a lower oxidation state. So, for example, if the reactant is having oxidation state 3 in the reactants, then it will have 2 in the product formation. So, basically, higher oxidation state changes to a lower oxidation state. Another aspect is the process can be called as reduction if there is overall addition of hydrogen to the molecule. So you can see when carbonyl compounds they are converted into alcohols, we add hydrogen across this unsaturated carbon oxygen double bond. So that means addition of hydrogen is also called as reduction. Similarly, in this example, this is carbon nitrogen triple bond and nitriles they are converted into amines as the product by gaining 4 electrons across this carbon nitrogen double bond, and here also this is addition of hydrogen, therefore this is an example of reduction reaction. So reducing agent is the material which will reduce the different functional groups from one functional group to another functional group by addition of hydrogen. So higher the reduction potential of the matter, higher will be the rate of reduction. And we have already discussed about lithium aluminum hydride, alkoxy aluminate reagents, and today we will discuss about borohydride based complexes. Sodium borohydride was first prepared by Schlenger and Brown in the laboratory, and the advantage of sodium borohydride is that it is less reactive than lithium aluminum hydride. You have seen that in case of lithium aluminum hydride, it can produce almost all type of functions, but the sodium borohydride is a selective reducing agent, and this will reduce only aldehydes, ketones, or acid chlorides in presence of even other types of reducible functional groups which will not be affected. So that means if in a molecule we are having an aldehyde functional group and an ester functional group, sodium borohydride will reduce only aldehydic functional group. Ester group will not be affected. In that way, this is more selective as compared to lithium aluminum hydride, because lithium aluminum hydride will reduce both ester functional group as well as aldehydic functional group. So this is the advantage of lithium aluminum hydride over this is the advantage of sodium borohydride over lithium aluminum hydride. And then this sodium borohydride, uh, this can be used under aqueous conditions or alcoholic conditions because of its excellent solubility in these solvents. This is relatively less soluble in case of ether solvents. So therefore ethers they are not used for sodium borohydride reduction. And in the final step, hydrolysis of the borohydride complexes is done either with aqueous ammonium chloride or aqueous acetic acid or dilute mineral acid, which on hydrolysis will give us the final products. So as far as mechanism of sodium borohydride reduction is concerned, this is basically similar to what we have seen in case of lithium aluminum hydride. So only difference over here is the mechanism can be of two types. That what kind of complexes they are formed in the protic solvents, or what kind of complexes they are formed in the non-protic solvent. So in the first step, what happens is the sodium borohydride interacts with the carbonyl compound. That carbonyl compound may be aldehyde or a ketone. Now, when hydride from the sodium borohydride is shifted to this carbon of the carbonyl, that means this will create a negative charge on this oxygen, and sodium from the sodium borohydride will get attached to this oxygen. So when we are having a protic solvent, what will happen, that protic solvent, either water or ammonium chloride, will give its proton to the oxygen negative, and sodium hydroxide will be formed, and we will get the final product in presence of protic solvent through this mechanism. But if protic solvent is not there, then after the shifting of the hydrogen, when this is having oxygen is having negative charge and this is attached to sodium ion, this will attack the BH3 formed during the reaction, and we will get this type of boronic complex will be formed. And because no proton is available to the intermediate, then it will react with another molecule of the carbonyl compound, and we will get one hydride from here will be shifted to another molecule, and we will get these types of by alkoxy intermediates. Similarly, third molecule will give us this intermediate, another hydride will be shifted, and that hydride will be added to the third carbonyl compound. Then similarly, because here uh, one more hydride is available for interaction with the carbonyl compound, so by reaction of four carbonyl compound molecules, we will get these types of final boronic intermediates. So these on hydrolysis in presence of acidic medium, they are converted into alcohols. So final product in both the cases are same, but the mechanism involved in case of non-protic solvent or protic solvent is different in case of sodium borohydride reduction, and this process is more efficient and less time consuming as compared to non-protic solvent. But in case of reduction of some complex molecules, we require non-protic solvent which boil at high temperature. Then, as I have told you, that sodium borohydride is a selective reducing agent, and it selectively reduces aldehydes and ketones in presence of epoxides, esters, lactones, acids, nitriles, and nitrophones. And all these groups, they are not affected by the sodium borohydride. So, if we are having either aldehyde or ketone in the molecule, in addition of any of these functional groups, this functional group will not be affected, reduction of only aldehyde or ketone group will take place. So this is the selectivity of this sodium borohydride reagent. So for example, in case of 6-oxo alstophyllin, this one, you can see that this molecule is having this carbon-carbon double bond, this methoxy group, this N-methyl group, in addition to the aldehydic group. So sodium borohydride, when reacted in presence of ethyl alcohol as the solvent, no other group except this aldehydic group is reduced. So aldehyde will be reduced to the primary alcohol. Ketone will be reduced to the secondary alcohol. So you can see that this reaction is a selective reaction, that we will get products where only reduction of the aldehydic group is taking place, no other group is affected. And similarly, if we use lithium aluminum hydride over here, then reduction of this group will also take place. So that will affect carbon-carbon double bond also. Then another example you can see over here, we are having this amide group, then N-benzyl group over here in addition to the aldehyde group. And when sodium borohydride reduction of this compound is done, only reduction of the aldehyde group takes place to the primary alcohol. No other group is affected. So reduction of these groups does not take place. So that means sodium borohydride is a selective reagent for these types of transformations. Then another important example of selectivity of sodium borohydride reduction is in many types of substrates where we are having presence of esters or hydroxyl group which are alpha to the carbonyl, or we are having a carbohydrate residue in addition to the aldehydic and ketonic group, or we are having halogens in the alpha position. So in all these types of substrates, reduction of only ketonic or aldehydic group will take place, no other group will be affected. Similarly, aryl ketones and aryl aldehydes, they can also be easily reduced to the respective alcohols. Then selectivity is so much that if we are having an unconjugated ketone and a conjugated alpha beta unsaturated ketone or conjugated ketone present in the same molecule, the preference will be that the unconjugated aldehydes or ketones, they will be reduced preferably in comparison to conjugated carbonyl compounds. So you can see in this example, this is having dithiene system, as well as this is alpha beta unsaturated ketone, this is unconjugated ketone. So conjugated ketone and unconjugated ketone, and when sodium borohydride reduction is done, this ketone is reduced to the secondary alcohol, and this alpha beta unsaturated or conjugated ketone group is not affected by the sodium borohydride. So this is the selectivity of sodium borohydride reduction. And in addition to selectivity of functional group, this is selective in terms of stereochemistry also. This group is beta, the alpha group is beta. So the reduced hydroxyl group will be alpha, that is at the opposite side of the molecule. Then chemoselectivity, uh, sodium borohydride reduction also used for reductive removal of halides selectively without affecting other functional groups. So you can see in this molecule we are having bromide, we are having carbon nitrogen triple bond, nitriles, acetates, then esters. So all these types of functional groups, they are not affected by sodium borohydride. It selectively reduces the removal of this Br by hydrogen. So at this carbon, hydride will be added and this Br will be removed. And this again is a chemoselective reduction in case of sodium borohydride. Then as far as stereoselectivity is concerned, it has only moderate stereoselectivity. The anion tends to attack sterically hindered compounds from the least sterically hindered side of the molecule. So for example, if we are having this bicyclo 221 heptane 2-one molecule and we reduce it with sodium borohydride, the endo product is formed in 86% amount and exo product is formed in 14% yield only. So this is because the anion, that is hydride, will attack from the less hindered side of the molecule. So here this is the more hindered side, so that is why the hydrogen will attack, hydride ion of the sodium borohydride will attack from the less hindered side of the molecule. So that is why we are getting more of endo product in comparison to exo product, because here hydride is to add from the more hindered side of the. Then some important applications of sodium borohydride reduction. This can be used for the reduction of enamines, imines, and iminium salts. So, for example, and all these products which are found by reduction of these types of compounds, they are very useful in alkaloid synthesis and amino acid synthesis. For example, in the synthesis of indole alkaloid masbinine, so this is the amine unit present in the substrate which lead to the formation of this indole alkaloid masbinine. Now, if you see, this is indole moiety, methoxy group is present and methyl group is present. In addition, you are having amino group and the carboxylic ester group. So when this is reacted with the benzaldehyde in ethyl alcohol, you know that amines, they condense with aldehydes and ketones, and we will get carbon nitrogen double bonded compounds. And these types of compounds, they are called as amines, or these are called as shift bases also, right? Now these amines, when they are reduced with sodium borohydride in methanol as the solvent, then reduction of this carbon nitrogen double bond will take place, and we will get secondary amines as the product, and further reaction of this substrate will lead to the formation of this indole alkaloid masbinine. So this is very important step in synthesis of this indole alkaloid. Similarly, in this second example, you can see that we are having this ether moiety also and N-methyl moiety also, in addition to this carbon-carbon double bond. And when carbon-carbon double bond is having alpha group in the form of nitrogen, these types of compounds, they are called as enamines. So these enamines, they can be reduced selectively in presence of other functional groups, and this carbon-carbon double bond is reduced to carbon-carbon single bond in presence of sodium borohydride. So this is also an important step in the synthesis of opioid alkaloids. So these types of alkaloids, they are called as opioid alkaloids. Then another selectivity of sodium borohydride reduction is that amides, they are not reduced directly by sodium borohydride. If we will react sodium borohydride with an amide directly, it will not reduce it. But if we convert these amides with POCl3 to Willsmere reagent, so when POCl3 reacts with amide, then these types of salts, they are formed, which are called as Willsmere-Hague complex, or these are called as Willsmere complexes. So these complexes, because they are having carbon nitrogen double bond, they can be reduced by sodium borohydride to the respective amines as the product. So they can be amides, they can be indirectly converted into amines through these types of reactions, but directly amides, they are not reactive towards sodium borohydride. Similarly, anhydrides, which are similar to lactones or amides. Lactones, they are not having this additional carbonyl. So in anhydride, we are having an additional carbonyl group present. So partial reduction of anhydrides can take place in presence of sodium borohydride, and they can be ultimately converted into lactones. And here also the reaction is selective in nature. You can see over here that the compound is having an additional carbon-carbon double bond also, and that carbon-carbon double bond is intact in the product, that is lactone formed also. So that means here also sodium borohydride is acting as a selective reagent, which will reduce only partially this anhydride group to the lactone group. So that means one of the carbonyl will be converted into methylene group. So this is formed through first this type of intermediate is formed uh, by breaking of say this bond. We will get carboxylic acid, and this is reduced to alcohol. Then this will undergo cyclization to give with the removal of water, and we will get these types of lactones as the product. Then sodium borohydride can give us some other metal borohydrides, uh, which are even more selective, and in some cases more reactive towards complex organic molecules. So one such example is lithium borohydride, and lithium borohydride can be prepared by reaction of sodium borohydride with lithium bromide, and we will get lithium borohydride as the product. So lithium borohydride will reduce aldehydes, ketones, acid chlorides as well as epoxides, esters or lactones. So you can see that the reactivity of this borohydride is more towards some other function group also. Sodium borohydride has reduced only aldehyde, ketones or acid chlorides. Here lithium borohydride will reduce in addition epoxides also, esters also or lactones also. But this will not reduce carboxylic acids, nitriles or nitro compounds. So that means the lithium borohydride is also a selective reducing agent, but towards some other function groups like carboxylic acids, nitriles or nitro compounds. And like sodium borohydride, this is soluble in ether. Unlike sodium borohydride, lithium borohydride is soluble in ether and THF also. So that means we can use more acids, more solvents for different types of function group transformations. Then major use of lithium borohydride is in reduction of esters, when ester is the most reducible group in the molecule. So we can reduce esters selectively even in presence of carboxylic acids or nitriles or nitro compounds. These will not be affected, only ester will be reduced. So you can see few of the examples of lithium borohydride in the synthesis of citrioviral. You can see this is the molecule where you have different function groups present. Where this is dimethylphenyl silane group is present, triisopropyl silane oxy group is present, then ester group is present, acetate group is present. So out of these four different functional groups present in the molecule, lithium borohydride will reduce only acetate group, that is an ester group, or COET group, which is also an ester group, and this silane groups or silane oxy groups, they will not be affected. So this is the selectivity of lithium borohydride. So acetate group will be reduced to alcohol. This COAT group will be reduced to sulfur. Then in this example, uh, these types of molecule, oxazolidinone auxiliary. Here you can see that this is imidic linkage, and this is lactone group which is present, and only lactone group will be reduced, and we will get these types of alcohols on hydrolysis as the product. Then another important borohydride is zinc borohydride, and zinc borohydride is used for diastereoselective reduction of hydroxy or alkoxy carbonyl derivatives. So if we are having, say, alpha group as hydroxy or alkoxy group, this OPMB is, or oxygen paramethoxy benzyl group attached to this oxygen, and you can see that this group will not be affected, this group will not be affected, this carbon carbon double bond, or this carbon carbon double bond, or this carbon carbon double bond, they will not be affected. This uh, dimethyl tertiary siloxy group, that will not be reduced by zinc borohydride. Only reduction will take place at this carbonyl group. So you can see that even alpha beta unsaturated ketones, only 1,2 reduction will take place. So this is very important diastereoselectivity of the, and addition of the hydride will be anti in this case. Then another very important borohydride is the cerium borohydride, which is also known as Leach reagent. So when cerium salts they are reacted with sodium borohydride, cesium chloride is reacted with sodium borohydride, we will get cerium borohydride or Leach reagent is formed. And this Luce reagent is also a selective reagent for 1,2 reduction of conjugated aldehydes and ketones. So we have seen in case of sodium borohydride that alpha beta unsaturated ketones, they are not preferably reduced when ketone is present. So this can be used for 1,2 reduction of carbonyl group when we are having alpha beta unsaturated ketones, and other functional group like esters, they will not be affected. So this is again a high diastereoselectivity of the reagent, which is formed from the reaction of sodium borohydride and cesium chloride heptahydrate. So these are some of the applications of different types of selective hydride reagents, which we have discussed in different lectures before this lecture. Lithium aluminum hydride, I have already told you that it can reduce almost all type of function groups like aldehydes, ketones, acids, acid derivatives, nitriles, halides, or purgyl alcohols. So the selectivity of lithium aluminum hydride is very low. So to make it more selective, one or more of the hydride ions, they are replaced by alkoxy ions, and we will get a milder substituted lithium aluminum substituted hydrides, and they are more selective in comparison to lithium aluminum hydride. So trimethoxy lithium aluminum hydride or tritertiary lithium aluminum hydride, they are milder and more selective in comparison to lithium aluminum hydride. Similarly, I have told you that red alum, which is similar to lithium aluminum hydride, but it is again more selective than the lithium aluminum hydride. Sodium borohydride we have discussed, lithium borohydride, zinc borohydride, Luchel reagent we have discussed, then a number of boron reagent which we will discuss later on in the coming lectures. They are also more selective as compared to lithium aluminum hydride, or even in some cases than sodium borohydride. So these are the different references which have been used for preparing this lecture. Thank you very much.